Welcome! In this session, we'll explore LeetCode problem number 2099, find subsequence of length k with the largest sum. Together, we'll break down the problem, consider various approaches, and understand the optimal solution. Let's dive in. In this problem, you're given an integer array called nums and an integer k. The goal is to find a subsequence of nums that has exactly k elements and the largest possible sum. A subsequence differs from a subarray because the elements don't need to be contiguous, but they must retain their relative order from the original array. For the output, you need to return any valid subsequence that meets these conditions. The input constraints specify that nums can contain both positive and negative numbers, with values ranging from -100,000 to 100,000, and its length is between 1 and 1,000. The value of k will always be at least 1 and at most the length of nums. The output is an array representing the chosen subsequence. Let's explore some examples to understand this better. Here's the first example. Suppose nums is 2, 1, 3, 3, and k is 2. To solve this, we need to consider all subsequences of length 2 and calculate their sums. For instance, the subsequence 2, 1 has a sum of 3, while 2, 3 has a sum of 5. If we continue listing all possible subsequences, we'll find that 3, 3 has the maximum sum of 6. Since we only need to return one valid subsequence with the largest sum, the output here is 3, 3. Notice that the order of elements in the subsequence matches their order in the original array. Next, let's look at another example. Here, nums is -1, -2, 3, 4, and k is 3. Again, we consider all subsequences of length 3 and calculate their sums. For example, -1, -2, 3 has a sum of 0, while -1, -2, 4 results in a sum of 1. Among all possible subsequences, -1, 3, 4 gives the maximum sum of 6. Therefore, the output is -1, 3, 4. Notice that even though this array contains negative numbers, the subsequence with the largest sum includes those elements that contribute the most positively to the total. Now consider the example where nums is 3, 4, 3, 3, and k is 2. The subsequences of length 2 include 3, 4, 3, 3, and 4, 3, among others. Calculating their sums, 3, 4, and 4, 3 each have the largest sum of 7. Since the problem allows us to return any valid subsequence, either 3, 4, or 4, 3 would be acceptable as the output. This demonstrates that if there are multiple subsequences with the same maximum sum, you can return any one of them as long as the order of elements is preserved. Finally, let's discuss edge cases. If nums has only one element and k is 1, the output will always be that single element. For example, if nums is 5 and k is 1, the output is 5. If all elements in nums are negative, the result will include the k least negative values. For instance, if nums is -8, -3, -5, -1, and k is 2, the output is -3, -1. If all elements are positive, the subsequence will simply contain the k largest values in their original order. For example, if nums is 1, 2, 3, 4, and k is 2, the output is 3, 4. Lastly, if there are duplicates, you can return any valid subsequence that preserves the order of the largest k elements. For example, if nums is 3, 3, 3, 3, and k is 2, the output could be 3, 3. These scenarios highlight the flexibility of the problem while adhering to the constraints. To solve the problem of finding a subsequence of length k with the largest sum, we can begin by exploring different approaches. The brute force method is the most straightforward. Here, we generate all possible subsequences of length k, compute their sums, and identify the one with the highest value. While this approach is intuitive, it's computationally expensive due to the sheer number of combinations. The time complexity is exponential, as it involves generating c, n, k combinations and calculating their sums. This makes it impractical for larger arrays. A more efficient option is the optimized approach using sorting and index tracking. In this method, we first identify the k largest elements in the array, then track their original indices to maintain the relative order required for a subsequence. Afterward, the indices are sorted, and the subsequence is constructed based on these ordered indices. This strategy is significantly faster, as it avoids the combinatorial explosion of brute force while ensuring correctness. The intuition behind the optimized approach lies in recognizing that the subsequence with the largest sum must include the k largest elements from the array. However, since the subsequence must preserve the original order of elements, simply selecting the largest values is not enough. By keeping track of their indices, we ensure that the relative order is maintained when constructing the final subsequence. The efficiency of this method comes from the use of sorting, which dominates the time complexity at n log n. Extracting the k largest elements takes linear time relative to k, and sorting these k indices adds another k log k. Altogether, this approach is much more efficient than brute force, even for larger input sizes. This optimized strategy was chosen because it strikes the perfect balance between efficiency and simplicity. It can handle arrays with sizes up to 10^4, making it suitable for competitive programming. Additionally, the steps involved are clear and easy to implement, making it a robust and scalable solution. The key insight, or aha moment, in this problem is the realization that maintaining the relative order of elements is essential. It's not enough to simply identify the k largest elements, the solution also requires preserving their sequence as it appears in the original array. By leveraging indices to track this order, the challenge is addressed in an efficient and logical manner. Comparing the two approaches, brute force is conceptually simple but suffers from exponential complexity, making it impractical for real-world scenarios. The optimized approach, on the other hand, achieves an excellent balance of efficiency and simplicity. While alternatives like a heap-based method could slightly improve the runtime for smaller k values, the added complexity of managing heap operations makes it less desirable. Overall, the optimized approach is the ideal choice, providing a scalable, efficient, and easy-to-understand solution to this problem. We are given the task of finding a subsequence of length k from an array nums such that the sum of the elements in this subsequence is maximized. A critical requirement here is that the subsequence must preserve the order of elements as they appear in the original array. To solve this, we begin by parsing the input. First, we need to validate that k is within the allowable range, which is between 1 and the length of the array. Next, to keep track of the original indices of the elements while working with their values, we pair each element in nums with its index. For example, if nums is 3, 1, 4, 1, 5, this results in a list of tuples like 3, 0, 1, 1, 4, 2, 1, 3, 5, 4. Then, we sort this list of tuples based on the values of the elements in descending order. Using Python sorted function with a suitable key, the list becomes 5, 4, 4, 2, 3, 0, 1, 1, 1, 3. This prepares us to identify the largest values while still retaining their original positions in the array. Once we have the sorted list of tuples, the next step is to extract the first k elements. These tuples represent the k largest values from the array along with their original indices. For instance, if k is 3, the top k tuples would be 5, 4, 4, 2, 3, 0. However, since the subsequence must maintain the original order of elements as they appeared in nums, we need to sort these tuples by their original indices, which are the second elements in each tuple. Sorting 5, 4, 4, 2, 3, 0 by index results in 3, 0, 4, 2, 5, 4. Finally, we extract just the values from these tuples to form our subsequence. From 3, 0, 4, 2, 5, 4, the extracted subsequence is 3, 4, 5. This subsequence satisfies both the constraint of maintaining the original order and the condition of having the largest possible sum for a subsequence of length k. The algorithm then returns 3, 4, 5 as the output. This approach relies on a few key insights. First, sorting the selected elements by their original indices ensures that the subsequence preserves the order in which the elements appeared in the input array. Second, by first sorting the elements by value and then extracting the top k, we guarantee that the subsequence achieves the maximum possible sum. Third, separating the sorting operations into two distinct steps, one for values and one for indices, makes the algorithm both clear and efficient, reducing unnecessary computations. In terms of data structures, pairing values with their indices in an array of tuples allows us to easily switch between sorting by value and sorting by index. Sorting algorithms are employed twice, once to find the top k elements by value and a second time to reorder those elements by their indices. These steps ensure the correctness and efficiency of the solution. Finally, let's analyze the complexity of this algorithm. Sorting the array of tuples by value has a time complexity of O, n log n, where n is the length of the input array. Extracting the top k elements is a straightforward operation with a complexity of O, k. Sorting these k elements by their indices takes O, k log k. When combining these steps, the overall time complexity becomes O, n log n plus k log k. Since k is typically much smaller than n, the dominant term is O, n log n. This makes the algorithm highly efficient for most use cases. Now, let's consider some edge cases. If k is 1, the result is simply the largest element in the array. If all elements in the array are equal, the algorithm will still return k elements in their original order. For arrays containing negative numbers, the sorting step naturally handles them, so the algorithm remains accurate. Lastly, if k equals the length of the array, the result is the entire array itself, as all elements need to be included. These considerations ensure the robustness of the solution across a variety of scenarios. This Python implementation solves LeetCode problem number 2099, find subsequence of length k with the largest sum. The goal is to find a subsequence of length k from the input array nums such that the sum of the subsequence is maximized, while maintaining the order of elements as in the original array. First, we pair each number in nums with its index to preserve their positions. This is done using a list comprehension, resulting in a list of tuples where each tuple contains the number and its original index. This step is critical for maintaining the order in the final output. Next, we sort these tuples by the number's value in descending order. This ensures that the largest elements in the array are prioritized for selection. After sorting, we select the first k elements from the sorted list. These are the top k elements with the highest values. However, since the subsequence must maintain the original order, we sort these k elements by their original indices. This step reorders the elements to match their sequence in the initial array. Finally, we extract only the numbers from the reordered tuples to form the result. This is done using a list comprehension. The result is the desired subsequence of length k with the largest sum in the original order. The overall time complexity of this solution is dominated by the sorting operations. Sorting the entire list of tuples takes O, n log n, and sorting the top k elements takes O, k log k. Thus, the total complexity is O, n log n, where n is the length of the input array. This is efficient and appropriate for the problem's constraints. Here, we start by defining the method maxSubsequence, which takes an integer array nums and an integer k as inputs. The goal is to find a subsequence of length k that has the largest sum while maintaining the order of elements as they appear in the original array. To achieve this, we first pair each number with its index by creating a 2D array indexed nums. This allows us to keep track of each element's original position. Next, we sort the indexed nums array in descending order based on the values of the numbers. This ensures that the largest elements appear first. After sorting, we use the arrays.copyOfRange method to extract the top k elements, which represent the k largest values from the original array. At this stage, we have the top k elements, but they're not necessarily in the order they appeared in the input array. To restore the original order, we sort these top k elements by their original indices. Finally, we extract the numbers from the sorted top k array and store them in a new array called result. This array will hold the elements of the subsequence in the correct order as they appeared in the original input. For each element in top k, we retrieve the value using its first position and assign it to the result array. Once all elements are processed, the result array is returned as the final output. This ensures that we return a subsequence of length k that has the largest sum while preserving the relative order of elements from the input array. This implementation effectively balances the need for sorting, selection, and order preservation to solve the problem efficiently. Let's start with the first example where nums is 2, 1, 3, 3, and k is 2. First, we pair each number in the array with its respective index. This gives us a list of tuples where the first element is the number, and the second is its index, 2, 0, 1, 1, 3, 2, 3, 3. Next, we sort these pairs by the value of the numbers in descending order. After sorting, the list becomes 3, 2, 3, 3, 2, 0, 1, 1, placing the largest numbers at the front. With the numbers sorted, we can now take the first k elements from this list. Since k is 2, we select the top two pairs, 3, 2, 3, 3. Now that we have the top k elements, the next step is to sort these pairs by their original indices. This step ensures that the sequence maintains the order it had in the original array. In this case, the list 3, 2, 3, 3 is already sorted by indices, so no changes are needed. Finally, we extract just the numbers from these pairs to form the result. From the pairs, we take the first element of each tuple, resulting in 3, 3. This is our output for the first example. Moving on to the next example, nums is -1, -2, 3, 4, and k is 3. As before, we start by pairing each number with its index, giving us -1, 0, -2, 1, 3, 2, 4, 3. The next step is to sort these pairs by the value of the numbers in descending order. After sorting, we get 4, 3, 3, 2, -1, 0, -2, 1. This ensures that the largest numbers appear at the start of the list. From here, we select the top k elements, which in this case is the first three pairs, 4, 3, 3, 2, -1, 0. To restore the order of these elements based on their original indices, we sort this subset by the second value in each tuple. After sorting by indices, we get -1, 0, 3, 2, 4, 3. The final step is to extract the numbers from these pairs. From the sorted pairs, we take only the numbers, resulting in the array -1, 3, 4. This is the output for the second example. Now, let's look at the third example where nums is 6, 4, 2, 8, 10, and k is 4. First, we pair each number with its index. The resulting list of pairs is 6, 0, 4, 1, 2, 2, 8, 3, 10, 4. As before, we sort these pairs by the value of the numbers in descending order. After sorting, the list becomes 10, 4, 8, 3, 6, 0, 4, 1, 2, 2, placing the largest numbers at the front. From this sorted list, we select the first k elements. Since k is 4, we take the top four pairs, 10, 4, 8, 3, 6, 0, 4, 1. Next, we sort these pairs by their original indices to restore the order from the input array. After sorting by indices, the list becomes 6, 0, 4, 1, 8, 3, 10, 4. Finally, we extract the numbers from these pairs, resulting in 6, 4, 8, 10. This is the output for the third example. By following this systematic process, we ensure that we find the subsequence of length k with the largest sum while maintaining the correct order from the input array. To analyze the time complexity of this solution, we break it down into individual steps. First, we pair each number in the array with its index using list comprehension. This involves iterating through the entire array of size n, which takes n time. Next, we sort these pairs by their values in descending order. Sorting a list of size n using Python's timsort algorithm has a time complexity of n*log n. After sorting, we select the top k elements from the list. This slicing operation is efficient and takes k time, as it simply retrieves the first k elements from the already sorted list. After selecting the top k elements, we sort these pairs by their original indices to preserve the order of appearance from the input array. Sorting a list of size k has a time complexity of k*log k, since Python's sort function is used. Once sorted, we extract the numbers from these pairs to form the final result. This step involves iterating through the list of size k, which takes k time. Combining all these steps, the total time complexity is the sum of n*log n, k*log k, and k, with the dominant term being n*log n. Therefore, the overall time complexity for the solution is n*log n. Now let's evaluate the space complexity. The first major component is the auxiliary space used to store the indexed _nums list, which contains n pairs of values and indices. This requires n space. Additionally, Python's sorting algorithm, timsort, requires O(n) auxiliary memory in the worst case. Next, the top_k list, which stores k pairs of values and indices, takes up O(k) space. Finally, the output list, which contains the subsequence of length k, also requires O(k) space. When we sum all these contributions, the total space complexity is dominated by the O(n) space used for indexed_nums and sorting. Hence, the overall space complexity is O(n). Let's discuss the best, average, and worst-case scenarios for this algorithm. Regardless of the input structure, even if all numbers are identical, the algorithm performs the same steps, so the time complexity remains O(n*log n, and the space complexity remains O(n). To compare with a brute force approach, generating all subsequences of length k and calculating their sums would take O(n)k time, which is exponential and impractical for large n. In contrast, this optimized solution leverages sorting and indexing to reduce the time complexity to O(n*log n, and the space complexity to O(n). This balance of efficiency in time and space makes the algorithm well suited for large inputs, offering a significant improvement over naive methods. Let's start by discussing some common mistakes that can occur while solving this problem. The first is sorting the entire array without tracking the original indices. While sorting helps identify the largest k elements, it's essential to keep track of their positions in the input array because the problem requires the subsequence to maintain the relative order of elements. Another mistake is choosing the top k elements without resorting them by their original order. This can lead to subsequences that don't follow the input's relative order, which violates the problem's constraints. Additionally, attempting a brute force approach by exploring all possible subsequences of length k can be tempting, but this method is highly inefficient for large inputs due to its combinatorial complexity. Finally, it's important to understand the difference between a subsequence and a subarray. A subsequence does not need to be contiguous, so its elements can be scattered across the array as long as their original order is preserved. Now, handling edge cases is another crucial aspect of this problem. For example, when k is 1, when the array contains duplicate values, or when all elements are negative, solutions can fail if these scenarios aren't explicitly tested. Always include these edge cases in your testing to avoid unexpected errors. From an interview perspective, this problem tests your ability to combine sorting with index tracking. It's not just about finding the largest k elements but doing so efficiently while adhering to the constraints. Optimizing your approach involves focusing only on the necessary elements instead of processing the entire input repeatedly. Additionally, be prepared to discuss how your solution handles small inputs, duplicate values, and negative numbers. Interviewers might also challenge you with follow-up questions, such as modifying the problem to find the subsequence with the smallest sum or dynamically adjusting k. These variations test your adaptability and understanding of the core logic. This problem shares similarities with other challenges on LeetCode, which can help you build a stronger foundation. For instance, LeetCode 658, which involves finding the k closest elements, requires careful index tracking and sorting, much like this problem. LeetCode 1389 tests your ability to maintain the relative ordering of elements, and LeetCode 300 focuses on subsequences but with the goal of finding the longest increasing one. Another related problem is LeetCode 1985, which involves selecting the kth largest element efficiently. When it comes to solving this problem, the optimal approach involves sorting and selecting. You pair each element with its index, sort by the element's value, select the top k elements, and then resort these by their original indices to preserve order. This approach is efficient, with a complexity of O(n)log n, and while it requires extra space for index tracking, it's straightforward and effective. An alternative solution uses a heap-based approach, which can be particularly useful for very large inputs when k is small. By maintaining a max heap of the top k elements and their indices, you can achieve a complexity of O(n)log k. While this method is slightly more complex to implement compared to sorting, it can be faster in certain scenarios. The brute force approach, on the other hand, involves generating all possible subsequences of length k and calculating their sums. While simple to implement for small inputs, this method is highly inefficient for larger arrays due to its combinatorial complexity of O(n)k. Each approach has its trade-offs, so it's essential to choose the one that best balances efficiency and simplicity based on the problem constraints and input size. Great work! To summarize, we solved the problem by leveraging sorting and index tracking to find the optimal subsequence efficiently. Remember the key takeaways and apply these principles in similar problems. Thanks for watching. Be sure to like and subscribe for more problem-solving guides. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!